it turns out that you don't need to stop at the number 5. This was understood by Felix Klein at the end of the 1800s. And what he realized was that these Platonic solids, what they are really coming from, they're coming from certain ways of tiling the sphere. The sphere is a positively curved surface. And what he discovered was that if you want to make more interesting tilings, the only thing you have to do is you have to abandon the sphere. You can use hexagons to tile the plane. If you go from a curved space, a positively curved space like the sphere, to a flat space like the plane, you can make more tilings. And in fact, if you go to a negatively curved space, which is what's being drawn here, you can make many more exotic tilings. In fact, most of the tilings of surfaces come from spaces of negative curvature. So I got some help from some people in the audience to illustrate this. So I gave them some triangles. Helpers put together 5 triangles at a vertex, and they got the dodecahedron. And here they put together 4 triangles at a vertex, and lo and behold, they've discovered the Pythagorean secret. This is the octahedron. It's a variant of the cube. So this is what you get if you make 3 triangles come together at a vertex. So that's 3, 4, and 5. If we go to 6, if you try to put 6 triangles together, you see it no longer closes up and forms a closed figure like the dodecahedron. You get something that's flat and flexible if you put 6 together. But the most interesting is what happens if you try to put 7 together. Here's 7 triangles trying to fit together, and you see you can't flatten it out. That's negative curvature. And if you try to put them together to make some sort of closed shape, you get this quite complicated, hyper-flexible thing with many, many triangles in a very small region. This is what it looks like if you try to build a negatively curved surface. So it's very simple. You just try to put together triangles so that 7 come to a vertex instead of the familiar 6. And you get this very wobbly shape. And what Klein realized is that shape makes perfect sense. It fits together without any of this wobbling if we put it in a space of negative curvature. Let me say a word about these shapes, the sphere and then the plane and then this space of negative curvature. So the first thing to know is that 2-dimensional surfaces have been classified for a long time. We know what the basic shapes are of closed surfaces. There's a sphere, and then there's a donut, then there's a sort of 2-hole donut, a 3-hole pretzel-like shape, and so on. These surfaces are classified by one number called the genus, which is sort of the number of holes. So what do these shapes have to do with these tiles? So if you have a square tile, the square tiles like to be put together into flat shapes, and you can't use a square tile to build a sphere, but you can use it to build a torus. You see, you put 4 of these tiles together and wrap them up to make a cylinder, and then you glue opposite ends of the cylinder together. And you can't really do that without distortion in space, but if you did, what you would get is a torus, a 1-hole shape. So I'm looking here at a 1-hole shape from the top, and it's being built out of 8 squares. There's 4 squares on top, and there's 4 squares underneath. So squares can be used to build a surface of genus 1, and in that way we can get beyond spheres, which are the limitation of the Platonic solids. Is that in the same way, you can put together 8 pentagons to make a surface of genus 2. So this is a top view of a surface of genus 2, and it's being built. There's 4 pentagons on the top and 4 pentagons on the bottom. Now, what do I mean by a pentagon? I just mean if you follow this edge, you see 1, 2, 3, 4, 5 sides. But the beautiful thing is that in non-Euclidean geometry, in a space of negative curvature in a negatively curved plane, you can find a right-angled figure that has 5 sides of equal length. There are regular pentagons in negatively curved space. So here's a surface of genus 3, and here is the corresponding tiling. This surface can be built out of 24 figures. If we allow ourselves these more complicated surfaces, then there are more Platonic solids. This is a new Platonic solid. It's built not out of pentagons, but out of 7-sided figures. The question Klein asked is, what is the underlying avatar of all of these different Platonic solids? Can we find a single motif which is giving rise to all these shapes? And what he discovered is that the answer is yes, and that single motif is something we're all familiar with. It's what's called braids. A piece of rope is obtained by many fine strands winding around each other. Mathematically, a braid is a shape or a topological pattern of parallel strings that are allowed to wind around each other. And so here you see the typical braiding pattern that if you take 4 pieces of leather or 4 strands of hair, you can wind them around each other and make this periodic shape. And the shape is built up by doing very simple things. You take 2 strands and you wrap them around each other, and then you wrap 2 other strands around each other, and so on. What do braids have to do with mathematics? What Klein realized, if you have a polynomial and it has some roots, maybe it has 4 roots, A, B, C, and D, these 4 roots can be thought of as the 4 strands of a braid. And if the polynomial changes without its roots ever colliding with each other, then as you move around, changing the polynomial, you can imagine that the roots move around at the same time and they braid with each other. They give one of these complicated shapes. More precisely, there's a way to associate to every polynomial some kind of a surface, and then from that surface we get one of these Platonic solids, and everything is dictated by picking some number is the secondary motif for the symmetry, and if we pick the number to be 5, we get the dodecahedron, but if we pick the number to be 7, we get this surface of genus 3 and some fancy way of tiling it using heptagons. So the Platonic solids turn out to go on, and the main obstruction to people discovering that they go on was just to jump from the idea of shapes that are just spheres to shapes that are more complicated. And in the world of surfaces, there's only one simple way in which you can make the surface more complicated. You just keep adding handles.